Okay, good afternoon. My screen is visible. Hello.
Yes, sir.
Yeah. Why are coming way so late? I scheduled at 1 o'clock. Now it is 1:15. Still, many people are not attended. There are any other works? They will come. Hello. Okay, see this HVDC transmission second unit. There is a converter circuits. So just previous class briefly I explained the syllabus also. Now we'll see in detail of syllabus as well as the first topic. Second unit is a converter circuit. It consisting of properties of converter circuit, analysis of bridge converters, with and without overlap. These are the topics in the second unit. Different kinds of arrangements. Now there is a bridge, full bridge, something like that, and even three phases. Before analyzing the circuit, we'll briefly discuss converters and analysis of bridge converters with grid control and with and without overlap angles. There is a grid circuit, 6 pulse converters with overlap and without overlap. Then equivalent circuit of a rectifier as well as the inverter, and the operation in both sides, the rectifier operation and inversion operation. So these are the topics need to cover in this unit, and we'll see the introduction first. This already we know that HVDC transmission we required as a two converters. That is, one is a rectifier station, another one is a inverter station. So in the rectifier station it will convert AC to DC, and in the inverter station it will convert DC to AC. Mainly consist of two stations. These are the two stations, rectifier and inverter station. All the converters normally in HVDC 12 pulse bridge converters are used. That is already mentioned. Instead of using 6 pulse converter, only analysis purpose we are using as a 6 pulse converter, but practically in HVDC system and all we are using as a 12 pulse converters. So by connecting two 6 pulse converters in series will form as a 12 pulse converter. Both same converter, whether it is a rectifier converter or inverter, can operate both. That is, we mentioned by controlling the firing angle alpha, can act as a rectifier as well as the inverter, depends upon the alpha. If you are changing the alpha, automatically that converter can act as a rectifier or can act as a inverter mode of operation. If the alpha is less than 90 degree, it will act as a rectifier, and alpha is greater than 90 degree, it acts as an inverter mode of operation. That's what we mentioned. That is already we know in case of single phase controllers or a three phase controllers. All these are not forced commutator circuit. These are the line commutated circuit. So that is a LCC. This is a simple word we need to use here. LCC circuit means line commutated converters. Here line commutated converters is natural commutation only. That's why whatever rectifiers we studied, same thing will come across here. But inverter station also will act as a rectifier station only. Depends upon the firing angle. If alpha is greater than 90 degrees, automatically same controller can act as a rectifier as well as the inverter based on the firing angle. There is a subject with the understanding of the converter principles and the steady state relationship which exists between the various parameters involved in this steady state process. So all these parameters we'll discuss. Converter have two types. One is a main circuit through which the high power flows. Because normally the converter means there is a transformer also you need to connect, because these are all in high rating applications. Main circuit with high power flows is one circuit. That will consisting of a converter transformer, because that total setup I am telling. There is a converter transformer as well as the thyristor walls and bus bars, series reactors. So if any HVDC converter, if you see that these are the in general circuit will be like this. So there is a source side, and here is a transformer also will be there, and there is a walls, and after that the output we are connecting as a large reactor. That reactor is very large, even up to 1 Henry also you can use it. For small 0.01 millihenry and so on, we will get as a little bit larger size, but you can imagine if it is a 1 Henry inductor, it is a very large inductor, so that output voltage will remain in the constant and ripple you can able to minimize. So that is the reason. And we also observed in the previous case the effect of that inductor, large inductor in the load side, that is in series with the converter, or a smoothing inductor we call it as. So these are the components we have: transformer and walls and bus bars, and then series reactors. Protection circuit for the firing or blocking of the walls is designed in the sequence and monitoring it. So that means the firing circuit, whether it is a device has to fire or a device has to turn off, that will be, there is a control and protection circuit will be there for the desired sequence. Here the sequence also very important. Once if you aware that in the 3-phase full control rectifier, there you can see sequence will be, we mentioned there, positive group devices are 135 and negative group devices are 246. In that aspect 462. In that aspect we can observe that the sequence of conduction is 6 1 1 2 2 3 3 4 4 5 5 6 and 6 1 cycle will be repeated like that. So this will be monitored. There is a desired sequence as well as the conduction. The main circuit of converters in HVDC terminal station made up of series connected wire. This is also very oftenly I quoted many number of times. Here this there is a number of devices are connected in a series to get it as a voltage level, or connected in parallel to meet as a current demand. So this is also on the converter station need to connect number of thyristor walls are in series between converter and transformer, and then DC switchyard. So there is a wall will be placed between the converter, that means converter consisting of a walls, and this side there is a transformer will be there, and then DC switchyard will be there. In between there is a converter, and the 6 pulse bridge converter is arranged in the 3 limbs. The 3 legs we are using, each leg consisting of 2 devices. One is upper, another one is lower. Upper will be forward bias whenever that corresponding phase will be more positive. Lower will be forward bias when that particular corresponding phase will be more negative. So in that aspect it is going to make forward and reverse bias. See that this is a thyristor, and here is another thyristor, because in a limb we have something as a phase. So let it be, this is a phase. So this one is a 4, let us assume that. So whenever a phase is more positive, then this will be forward bias. If a phase is more negative, this will be forward bias. So in that way we have as a 3 limbs like this. Another set also will be there. This one will be coming here, and another one will be here. So what it will be is, so we'll get it as a more positive voltage, that particular device will conduct more negative voltage, and so on. So you will get it as a conduction sequence. So this will be 6 pulse converter, it consisting of a 3 limbs and each will be vertical structure. There is just now I drawn that. AC supply is given from 3 secondary leads of a converter transformer, because in a converter this primary side means converter input side, what I mentioned, there is a something phase here, let it be like that. We have 3 phases, no, there we have to connect as a transformers. So let it be as a star delta or delta, because based on your 6 pulse or 12 pulse, like that we can connect the transformer. So transformer primary is connected to the source and secondary is connected to the valve. So secondary of the transformer is connected to as a valve. So that means there is a 6 valves are fired in a different sequence. DC output is obtained at the terminals of a 6 pulses operated at a rectifying mode, because the transformer is this side. Similarly, DC output voltage waveform for 6 pulse converter has 6 pulses per cycle of AC. 6 pulse converter itself we can define one full cycle of AC supply will get 6 pulses in the output. That means output is a DC, and with respect to the AC source, you will get it as a 6 pulses in the output. So that is the pulses we are going to generate in the 6 pulse converter. Similarly, 12 pulse converter has two 6 pulse converter connected in series. So just a minute. Yeah, come.
ఎంత ఫ్యాకల్టీ ఉన్నారు అందులో ఎవరిని ఇవ్వమంటాను అని అడుగుతున్నారు.
అదే అతను ఉన్నాడు కదా,
సుధాకర్ బాబు గారేమో ఇంత ఫ్యాకల్టీ రేషియోలో చేశాను అని అడిగారంట.
ఆయన చేస్తాడట.
అది ఇంతకుముందు చేశాను, అది ఐడియా ఉంది అని నన్ను అడిగారు. మేడం అడిగితే నేను ఫ్యాకల్టీ క్రైటీరియా చేశాను ఇంతకుముందు, నో ఇష్యూ అన్నారంట. ఫ్యాకల్టీ క్రైటీరియాలో వేద్దాం అనుకున్నాను. దీప్తి మేడంని చైతన్య సార్ని వేస్తే హరికృష్ణ సార్ని మళ్ళీ రివర్ట్ బ్యాక్ చేసుకోవాల్సి వస్తుంది, ఎందుకంటే ఎక్కువ మంది
ఇద్దరక్కర్లేదు, అతన్ని దీప్తిని మన సరిపోదు.
చైతన్య సార్ని అక్కడ పంపించేసిందని చెప్పండి. ఓకే, ఒకవేళ హరికృష్ణ సార్ని పంపించేస్తాను, చైతన్య గారిని
లేదు, హరికృష్ణ ఉంచేసి ఆ కొత్త ఎందుకు దీప్తిని పెట్టేసి హరికృష్ణను మనకే ఉంచేసి.
ఓకే.
So this 12 pulse converter has two 6 pulse converters connected in series, and that will be happen, here the transformer connection is very essential. One must be star and delta, another must be star star. There is a phase shift of 30 degrees is required in this case. That is the reason one 6 pulse converter connected in series, second one, there is a first one is a star delta and then another one is a star star. This is the arrangement is required for the 12 pulse converter. So there is a phase shift of secondary in 3 phase AC voltage, that is a 30 degrees phase shift is required. That is the reason. So DC waveform, now once if we are using as a 12 pulse converter, totally you will get it as a 30 degree phase shift. Each pulse will be conducting for 30 degrees. That means 360 by 12. That will give as a 30 degrees, whereas in the 6 pulse converter there is a 360 by 6 will give as a the 60 degrees duration. So that means if you are increasing the pulse number, automatically your waveform will be in this smoother fashion, as well as the ripple frequency will be high. Therefore ripple magnitude will be minimized and filtering requirement also will be minimized if you use this. But beyond 12 pulse converter, it is very complicated to design as a firing circuits, because here very lesser time duration we need to change over the device, and also will be overlap is going to be takes place. Even for 3 pulse for 6 pulse converter itself, we have some cases 4 devices will conduct. So all 4 devices is fired among 6 devices. Some cases 4 devices also will be fired based on the overlap angle. If overlap angle is greater than 60 degree and all, it is complicated to design that for beyond the 12 pulse converter. That is why generally you don't prefer beyond this level. And the large smoothing reactor, as I mentioned, this reactor is very large. You can see that 0.2 Henry to 1 Henry. This is the size of this will be very large and costly, and it is necessary in the DC side pole smoothing of the DC current waveform. As you are aware that your output, whatever you are getting, that one is not exactly as a DC straight line in fashion. There is a lot of harmonics involved in it. To minimize that, what we are using is that waveform we are passing through the reactor, so that your output is going to be minimized. So that means harmonic content is going to be minimized. So that is the improvement by using as a reactor in that. So now we'll see the wall characteristics. The wall is nothing but a simply thyristor or a switch. So, but here just the diagram shows that this one will be a very olden days they used this mercury arc wall. So this is the symbol of mercury arc wall. Now this generally they already replaced with thyristor. So this they don't use nowadays. They will use as a thyristor. So that's what I mentioned here. Mercury arc wall lamps. So there is a uncontrolled device of diodes and control valves for any type, whether it is a mercury arc or solid state shown in the figure B and C. So now you can see that this is uncontrolled. This one is a control devices, but generally we'll use as a control device instead of mercury arc valves. And there is a characteristics of that diode also mentioned under forward current with voltage is 0. So when voltage is 0 and current is there, and vice versa, when the voltage is present and current is 0. So these aspects you can simply identify switching on and switching off the device instant. As you know that when the switch is on, what is the voltage across the device? 0 or preferably very negligible. Under ideal condition, straight away we can say it is 0. Similarly, when the switch is open, then voltage across the device will be the source. So that way we can easily identify the characteristics of switch. And then a wall normally conducts in only one direction. So here already mentioned in case of thyristor, valve is going to be conduct from anode to cathode, or in the only one direction, or you can say that because this device is unidirectional device, it will conduct only from anode to cathode, and that is the reason I mentioned here only one direction, that to anode to cathode. While it is conducting, there is a small drop across it. So once the device is conducting, this also known to you, once any device is conducting, voltage across the device is very less, that will be 1 to 1.5 or 2 volts voltage drop across that. But that will slightly vary, depends on the rating of the device also. But normal case, what we discussed in power electronics and all, it is very less. But normally, if you go to HVDC transmission, the voltages drops, all these things little bit increases because very high rating of devices we are using. So that is the reason we can say that under conduction voltage drop across the device is going to be high under HVDC transmission. Current and voltages are in forward direction and are taken as a positive because once the device is conducting, the forward voltage drop in mercury arc walls is in the 20 to 50 volts. Even for higher values, if the HV value is increases, let it be it is a 40 to 50. But these are mercury arc walls that that is little bit technology is very poor, and they used as mercury arc walls this much drop. But now later they replaced with thyristors. That won't be much this much voltage. It is very negligible amount of voltage. And there is abnormal operation. Wall can be sustained as a comparatively high voltage in a reverse direction without conducting. except for the negligible leakage current. That means under abnormal operation, suppose peak inverse voltage or reverse voltage is it can be withstand. If it is not able to withstand, the reverse breakdown is going to be takes place, that leads the device is going to be conduct. That should not be happen actually. If it conduct, there is no meaning of control there. Automatically, if the reverse voltage is beyond that specified value under that operation, automatically the device is going to be conduct. That is what in the characteristics of SCR we seen. Forward breakover voltage and then reverse breakover voltage. If that voltage is beyond certain level, automatically device is going to be conduct. So that is what here what we need to do is under abnormal operation the device has to withstand in the reverse voltage without conducting, except very small leakage. That also based on the junction 1 and junction 3 there is a small leakage current is going to be takes place. So that is another problem here. The rated current of HVDC may be hundreds or thousands amperes also, because the normal thyristor rating itself you can see up to 3 kilo amperes of current can withstand. That is the HVDC valves may be 100 amperes or 1000 amperes, and the peak inverse voltage is a 50 to 150 kV. In comparison, you can see that inverse leakage current and forward voltage drop are negligible, because I told no in the voltage drop or under reverse condition also leakage current at junction 1 and junction 3 that will be as a minimum. So simply under these conditions we can able to neglect that. That is a forward voltage drop is neglected. Hence, the idealized VI characteristics of a diode, that is already I shown you in the previous diode characteristics. We can observe this diagram. Forward current at 0 voltage. You can see this one. There is a current. This one is a forward current at 0 voltage. So this voltage is a 0 axis. We'll get it as a forward current. Similarly, inverse voltage, this one is inverse voltage at 0 current. So this is a 0 current, either it is 0 voltage or a 0 current based on that forward current or a inverse voltage. So this is the ideal characteristics of a diode. Another one is the properties of a converter circuit. So in the consideration, you can see that waveforms of the voltage and currents and their magnitude in terms of the voltage, that is a DC voltage and DC current you can mention. From these data, you can find the required volt ampere rating of a valve and transformers. So why this is, if any particular application you want to use as a thyristor, we should know that what is the requirement of the volt ampere voltage rating of the SCR. Otherwise, if our demand or our application is very high condition, but if you use as a thyristors are in the low rating, the reliability will go down, and also sometimes the devices also will fail. To overcome that problem, what we will do is we have to decide volt ampere rating of the valves, means thyristor, nothing else. So and as well as the transformer, because transformer also you are using here compulsory we need to use as a transformer, and followed by there is a source, then transformer, then converter circuit that consisting of a valves, and then load side is a in series with the converter there is a large inductor you need to connect, and finally you'll connect it to the load side. So that is what rating we need to decide, valve rating as well as the transformer rating. Then the DC power PD is equal to VD into ID. So based on that we are going to decide what is the rating of valve and transformer. So volt ampere rating of valve is taken in the product of average current and inverse voltage. So these are the, you can see that average current and peak inverse voltage of that particular device. So that will decide what is the rating of volt ampere rating of a device. And similarly, transformer winding case, what we will do is, it is a product of RMS voltage and RMS current. So that means VRMS into IRMS I consider as a volt ampere rating of a device. I mean transformer in case of transformer case VRMS into IRMS. But whereas in case of device, we can see that average current and peak inverse voltage. So that will decide the volt ampere rating of a valve. And there is assumptions also we need to consider. This oftenly we discussed many times. There is a we need to idealize the walls. In addition to idealize the walls, what we need to do is we idealize the AC source and transformer and the loads as follows. That means to idealize your wall values, we have to idealize means some of the assumptions we have to consider for AC source side as a transformer side and load side. So these are the three things we need to consider. What is the source side is, source has no impedance and delivers the constant voltage of a sinusoidal waveform and constant frequency. This is very essential in the source side. But practically, if we speak, it may not be as a no impedance case. There is impedance. We have as a source resistor because a lot of wires are there, and we have to connect that transformers to particular instant. That is the reason we can see that what we will do is no impedance in the source side. That shows what voltage drop in the source is going to be minimized as much as possible once if you neglect that impedance. But practically there is impedance. If you consider that impedance, what we discussed in power electronics, that come into the picture. There is a no impedance means the output we can change the load also, but source will maintain as a constant voltage. If polyphase is delivers balanced voltage, that is another assumption. If it is a single phase is that one, or polyphase case it delivers as a balanced voltage. And transformer has no leakage impedance nor existing as a admittance. So this is also, you just neglect the leakage impedance. And DC loads have infinite inductance because the load side they may have as a highly inductive loads. So from which it follows the direct current is constant, that is free from ripple. This all about some more assumptions also there. There is a HVDC converters have a large DC smoothing reactor that I already mentioned, 0.2 to 1 Henry. So that much large reactor is required, and it is reasonably accurate for converters having 6 or more pulses per cycle. So if more pulses per cycle means that is a more than 6, let it be, or in general case HVDC there is a 12 pulse converters and all will use. And the current is assumed free from ripple. So how you will get this free from ripple? That is what we used as a smoothing reactor. So these all assumptions, the current is assumed ripple free, that will obtain wall side as well as a smoothing reactor. So these are the some of things are assumptions. And different kinds of arrangements you can see. There is a one is half wave rectifier. So because just before going to, normally we are using as a 6 pulse converter or 3 pulse bridge rectifiers we are using in the HVDC transmission. And then what is the impact of what you call it as a pulse number. So once if your pulse number is increases, then what will happen? Automatically there is a effect on that output voltage. You can see this is also one important. That is the reason we are going to higher pulse number rather than the previous one. Once if you are increasing the pulse number, automatically you can get it as a ripple magnitude will decreases and output voltage will be improved, and hence we can go for as a higher pulse number, but it cannot be beyond some certain level. You can see if it is used as a some pulse number logic, you can get it output voltage is this for 1 pulse converter, and for 2 pulse converter, yeah, this is the 2 pulse converter, and similarly 6 pulse converter you will get it as a 3 pulses. And then there is a little bit you want, you can show that ripple also further. You can consider for 6 pulse converter all uniform, just there is a gap here, but all pulses are uniform. And then if we go with 12 pulse converter, you get it as something like this. So this is the scenario by increasing the pulse number. So here once the pulse number increases, you can observe the waveform. We are getting very smoother wave, very high frequency of ripple, and the magnitudes output voltages are more, as well as waveform also is improved. So that is the reason we'll go for as a higher pulse number. Let it be. There is a half wave rectifier. So in this only one valve is there, source transformer, and then you connect one valve and then output side. So this is our half wave rectifier circuit. There is a transformer, any of the primary as well as the secondary, and after that it is connected to as a diode. So diode or a switch, general notation I am telling. Here is a controllable switch or normal switch. If it is a half wave rectifier, the how the analysis is going to be. Now there is a source, because transformer is connected between valve and source. So between valve and source only we connected as a transformer. So therefore you can get voltage across the device and voltage across the inductor and output voltage. All these things analysis will come here. And for positive off cycle, what will happen? Diode will be forward bias. Output is coming, same as the source. When the circuit is on, so this circuit is a simplest rectifier having one valve. So there is only one valve in a circuit, and that circuit will be simple. And there is a inherently intermittent, and therefore the circuit cannot be analyzed in the proper way and assumed of steady state condition. All other converter circuit can be and so analyzed. Only the thing is here, one pulse converter in general nowhere will be used in our normal applications, because very pulsating in nature. So that is the reason we can avoid this type of controllers. And both the direct current and direct voltage pulsate at the same frequency as alternating voltage. So this is normal. And if a transformer is placed between AC source and a valve, is usually necessary for obtaining the desired magnitude of a direct voltage. Direct current passes through the secondary winding. So once the transformer is already there in between source and then load, if any current, magnitude of the voltage and current passes through the secondary only, because this is the transformer, primary is connected to the source, and automatically whatever it draws the circuit, it is coming from the source only, secondary of a transformer. This circuit useful only for very small amount of power, because it is a one pulse converter only. So one pulse converter in a one full cycle of just a minute, one full cycle of AC supply, this will get it as a one pulse in a output. Yeah, so this is the one pulse converter, one full cycle of AC supply will get it as one. Another one is a full wave rectifier. So what is the difference between these two? There is a lot of differences are there. One thing we can remember, that one is a first device is there, and second device both has to conduct one by one during positive off cycle and during negative off cycle, and midpoint is connected to the load side. This voltage and this voltage will be the same, and neutral point is connected to the load, and after power circuit this one will be as a power circuit, and end of that you will get it as a inductor value. So inductor means you have to connect that then to smoother. So now we can see here VD voltage after the controller, and this will be as after reactor you can use it. So this way how these voltages will be obtained, and that is all purely based on your operation. So during positive off cycle and during negative off cycle you will get it, and finally our intention is to get it as a output in a DC terminal, let it be as a VDC. And now the waveforms you can notice here, the supply voltage is there, and then crest voltage or a peak voltage, another one is a VD voltage. So VD means this voltage. So these are the things need to be VD. Is it yeah, this one is a VD, and this also VD. This V will be capital and this one will be the small. Now we can see that there is a average area of these two. So you can see that this one will be the average, and this portion is a this portion VD, and upper side we can consider as a VG. So that way we'll get it as a full wave rectifier, and in that full wave rectifier there has two valves and one transformer with center tap secondary winding. That is the requirement. We notice during positive off cycle one device has to conduct, during negative off cycle some other device is going to conduct. The line to neutral secondary voltage, we noticed there E1 and E2 have the phase shift of 180 degrees are plotted. Why the phase shift of 180 degrees? You can see here there is a supply is a sinusoidal. Let this is a positive off cycle and then negative off cycle, and for positive off cycle somewhere alpha will start and it will conduct up to 180 degrees, and for negative off cycle suppose if it is a full, again you will get it as a another full cycle, otherwise you will get in this can say same as source or simple way. That's what there is a, this is 180 degrees, this is also will be 180. There is a phase shift of 180 degrees in this regard. So another one, the anode voltage of a valve V1 and V2 with respect to the neutral is equal to the E1 and E2 respectively. So when you are voltage you want to measure at valve 1 and valve 2 with respect to the neutral is equal to the E1 and E2 respectively. So that is the take care you need to consider. The difference in HVDC which appears across the reactor is represented by the vertical shading. So that means in the diagram we shown you horizontal and then vertical shading. The difference in HVDC which appears across the reactor, they are represented by the voltage sharing of the converter wheel. The waveform when valve is conducting, the full secondary voltage that is E1 minus E2 appear across the valve 1, and similarly another valve is turn off. Let it be there is a full bridge here, one valve is conducting. Suppose this is the problem of midpoint actually, but it is not there in the bridge type. In midpoint we can notice one thing, I will show the waveforms also. Let it be one valve is conducting, let valve 1 is conducting, valve 2 is open. If valve 2 is open, what is the voltage across the valve 2? That is entire secondary winding is connected to the valve 2. So therefore you will get it as a 2M is a peak inverse voltage, or vice versa. If valve 1 is open and valve 2 is conducting, the entire secondary is connected to the valve 1. So Vm sin omega t and Vm sin omega t, totally 2 Vm sin omega t, or let it be as a Vm 2 Vm, that is a reverse voltage appear across the valve. So that is the problem. That's what I mentioned here. Valve 2 is conducting full secondary voltage appear across the valve 1, or when valve 1 is conducting again appear across valve 2. That is will show the waveforms also. I think I shown in the previous slide. Yeah, so this is the thing we can see here, this 2 Vm. So that means when any of the device is conducting, automatically the total secondary winding is connected to the valve 1 or valve 2, depends on our conduction the devices. And this one small derivation, just you are finding what is the crest voltage or EM peak voltage. Now let compute that some of the parameter average voltage and all. Filtering voltage VD, average value of voltage is small VD, and the later consideration of the positive half cycle, the crest voltage is EM, and the frequency here is a 2 pulse converter. 1 by 2 pi is a full cycle of the frequency, or time 1 by 2 pi into 2, so that will give as a frequency. Let theta is equal to omega t, and you can integrate that portion, any of the off portion, you will get it as a 2 Vm by pi. That is the maximum any, because I used there is a diode, that is the reason I am not mentioned as a alpha or something. Just I consider omega t is equal to theta, and I integrate this, you will get voltage, average voltage is a 0.637 into M. From this M is equal to, I can get it in terms of the VD. VD is our average output voltage. Then you got it 1.571 VD. This is the EM value will be obtained. And the peak to peak ripple, that you can notice, M is nothing but a ripple, maximum peak to peak, no peak value 1.571 VD, and its frequency is a 2F. So what frequency it is a 2F is a inverse one. So where F is a frequency of the AC supply and peak inverse voltage is a 2 Vm, that is we'll get it as a 3.142. This frequency is a ripple frequency. How the ripple frequency is very high, even if it is 6 pulse converter, 6 times of that will get it as a ripple frequency. Now it is a 2 pulse converter, that's why I mentioned 2F is our ripple frequency. And then bridge type, you can see that it is only the same previous one, you can reverse and you can get it as another one, and you will make use of this set, and the output only thing is the negative voltage will be obtained here. So and here we will connect it as a source VD, and there is a neutral point also connected. This is one of the configuration. Different kinds of configuration for the 3-phase also will be there. Just for understanding before going to the our main analysis, we are able to understand this. And you can notice here what is the problem is overcome is here. Earlier once if we use as a midpoint, if any of the device is conducting, what other device will be 2 Vm peak inverse voltage, but now it is in the bridge fashion. We don't use any transformer over here, and that is the reason we'll get it as a Vm only our peak inverse voltage. So that is the another one. And then in a full bridge rectifier, just before slide, two valves are in midpoint circuit. What we used in the midpoint were reversed, and here you can place in the reverse the same devices, so that the anode instead of the cathode were in the common potential. There in the case of if you just see in the previous one, yeah, this one you can see, yeah, this one the cathodes are in the common potential, not anodes. But whereas here we can able to get it as anodes are the common potential. So these are the anodes are in the common potential one end, and that's what I mentioned, common potential. Nothing would be the change except the direction of the voltage. So that is the one thing. Further, the same transformer could feed the two pair of walls, another pair, because we formed as a bridge fashion, no? Two devices were coming from midpoint, they just reverse it, the common terminal will change, and another pair of walls, one pair of connection at midpoint, and other pair reversed as just discussed in the previous diagram. Now just we are replace that, then we'll make use of a bridge fashion. Each pair of walls could feed as a separate load with a common return, because the diagram itself we taken as a neutral point there, that is a point n. In other words, the rectifier would now be feeding as a 3-wire DC wire system. So that is a we'll get it as a 3-wire DC system will form, because we are connecting as a midpoint. And if current on both positive and negative sides were equal, then what will happen? Neutral conductor and the center tap transformer secondary winding would no longer be needed. So if the both is same, if the current on the positive as well as the negative sides were equal, then neutral conductor is not required in the center tap. And this results such ohmic in the single phase bridge rectifier. It is known as a two-way circuit also. So one half, because with midpoint n we consider we'll get it as one circuit, and with midpoint to the upper side if we consider, that will get it as another circuit. Therefore two-way circuit will form if you use as a bridge configuration in this. Now there is analysis of HVDC converters. Now there is some of the topics we need to cover. It is a thing is based on the pulse number, as we discussed why we need to increase the pulse number with one pulse if you use, what will happen, then you have to increase another pulse, like that p number of pulses we have to connect in parallel, so that what will happen, all these things will discuss in this pulse number area. And choice of converter configuration we need to discuss, how the walls are connected in the arrangement, how many walls are connected in series and how many are in parallel, what is the sequence of this. So all these things will come under the choice of converter configuration, and peak inverse voltage all we can able to derive there. And analysis of grid circuit, this is also called as a 6-pulse converter, full controlled bridge rectifier. Grid circuit is nothing but a 3-phase full controlled rectifier, or a 6-pulse converter, simple way we call it as it. And then converter bridge characteristics, because again bridge circuit characteristics, and then characteristics of the 12-pulse converter. Once if you complete this 6-pulse converter analysis, simply will make use of 2 6 pulses, and transformers are connected in star delta and then star star fashion, and we'll simply analyze that characteristics of a 12-pulse converter and detailed analysis of converter. So these are the things we need to discuss for analysis of HVDC converter, and we'll move on to the pulse number. What will happen if we are increasing as a pulse number in this area? So that we can see in the next class. It is all very small units. It will complete very soon. And once these topics if we covered, and with overlap and without overlap, this unit also going to finish. And if I have any doubt, you can ask me. But attendance, you take care. Total 41 members, but now today we have only 32, I think. You can give your you just join for the attendance sake also, at least. Okay, you can leave.